you might be able to, access certain objects using one policy and different objects using different policy. Another variation of the basic model is limited depth inheritance, and as the name suggests, that you will be able to get access to objects only, above you up to a certain depth or below you up to a certain depth. There's a limitation how many levels you can go. And to be able, to support this policy, we also need to do a little bit more work for this graph. And so the first thing, we assume that the access graph is layered. Many graphs are not, but it's not very difficult to modify one by adding additional nodes to make sure that this condition is true. And so what layered means that, intuitively there are layers, right? And we modify or we partition all nodes in the hierarchy into disjoint sets. And for example, we say if for each edge in the hierarchy, if there is an edge going from node A to node B, and if node A belongs to a certain level, then node B is going to belong to the next level. And then having this information, having those layers, we create an access graph where there is just one node per layer, and we kind of link them together. We create an edge. We create an edge going one way, and we create edges going the other way. And so in this case, if we have a key that can be derived one way and key that can be derived different way, you kind of for each user you give one starting point and another starting point, and everything in between can be derived for that user. But unfortunately, with this approach, the scheme is not collusion resilient. It means that if I have certain privileges, someone else has different privileges. We are able to combine those keys in such a way so that it's possible for us to get more information that each of us can get individually. And so this is, kind of future work to have a scheme that will work in collusion resilient manner for this particular model for limited depth inheritance. But if you consider all of these different access models, they will actually be very powerful, and the policies that you can support will be rather rich. And it's not just going one way or the other way. You can support a very rich set of policies for access hierarchies. And now I'm gonna switch to a little bit more algorithmic part of this talk, which deals with efficiency improvements. And so, as I said earlier, in this hierarchy, to be able to derive a key from one node to a different node, you have to traverse every node on the path. And in some cases, that particular graph can be long and skinny, so the depth of it can be pretty long. And it doesn't happen in many applications. For example, on average, if these are rows in our bad model, then you usually have constant number of levels, constant depth in this graph, how deep you want to go. But in certain other applications, such as manufacturing, when you have a lot of different components that have to interact with one another, and then this graph can become pretty large and pretty deep. And so in this case, in the worst case, the work that someone needs to do to derive a key to a certain object will be linear in the size of the graph. And for balanced trees, for example, it's going to be logarithmic, but in worst case scenario, it will be linear. And so to be able to avoid this, to be able to make this key derivation time shorter, we use a technique, so-called shortcut technique, that we add additional edges that still preserve the structure of the graph, they still preserve all relationship, but they will allow people to perform key derivation much faster because of those additional edges. And for now, let's assume that we're working with a tree of n nodes. And we have two different results actually. The first one is that if you add only a linear number of nodes, linear number of edges to the graph, then key derivation time will be guaranteed in log n steps. And this is double exponentially better than the linear time that we started with. And if we in here number of the edges introduced is asymptotically the same as number of nodes, so it's just a constant increase in space. But if you allow just a little bit more space to be used for the graph, and if we add n log n edges, that every node within this graph becomes reachable within 3 hops. So it's not a very large increase, but key derivation time is going to be much faster. It's going to be 3 hash functions, which is very fast. So these are some ideas how we do this, and I'm not going to go into very details because it becomes somewhat complicated. But I just want to give you an idea of what techniques we use. And the first definition that I'd like to remind is that we're working with a tree, that there's a notion of centroid. And a centroid is a node which, if you remove that node from the tree, it leaves no connected components of the tree that are larger than half of the original tree. So we kind of take one node, and all parts that remain will be twice as small as the original tree. And so the basic idea here is that we pick a particular node in the graph, and we're just going to look at subtree rooted at that node. And so the first thing that we do, we compute a centroid. So we know that partitions it into that actually partitions it into pieces that are at least half of the size. And then we take that node from that subtree and start the procedure again on the remaining. So we kind of make it smaller and smaller every time until it becomes empty. And this is just recursive procedure for a node, but it's used as a building block in the larger algorithm that I have. And so if you execute this basic procedure for every node in the graph, the number of edges that we add is n log n, and additional edges or any distance between any two nodes will be guaranteed logarithmic time. And so this is not the results that I promised earlier, but this is just the first step towards the goal. And other techniques that are used in this efficiency improvements is so-called centroid decomposition. And the way centroid decomposition works is that you take original tree and you compute a centroid and take it out. So you have remaining parts that are much smaller than the original tree, and then you recursively repeat this procedure, compute centroids of the smaller trees and remove them until the size of every tree remains 1, until we actually partition everything completely into separate nodes. And then you basically you record the sequence of those centroids that were used in that centroid decomposition. So this is not new, and it's very standard in people who work in algorithms area. But what we use here is not regular centroid decomposition, but so-called prematurely terminated. And so the idea is still the same, that you compute a centroid, remove it, then compute centroids of the remaining parts and remove it, but then we stop not when it's become of size 1, but we stop much earlier. So we stop